Well, good afternoon, everyone. And to start with, let me thank Armin and also the colleagues here for giving me the opportunity to talk some of our very recent work. And today I shall be going to talk about the role of quantum bias theorem, and in particular how one could apply in the context of quantum measurement, and possibly to use them in order to find out some of the contradiction that we see in classical domain to be resolved in the quantum domain. Okay, so here is the outline. By the way, how much time I have? Means it's like 40 minutes in total. Okay, very good. So I will try to be as concise as I can. So here is the outline. I start with a very brief intro of this quantum bias theorem, and then maybe going to show you some very trivial two examples to show you that how these two rules gives you two different results. And then I will be considering Frauchiger-Renner setup and also the Hardy setup. Mostly they have been used in the context of some paradoxes. And then I will conclude. Okay, so that is what it is. So let me now start with quantum bias rule. But here let me start with the classical analog. So here let's say I have some system which is maybe coming up as random variable like 0 and 1. And let's say there is a stochastic evolution going on, and let's say these are the conditional probability that tells you like starting from 0s what is the probability you will get on 0a on the other side, and so also for 1 here. Okay, so in this particular scenario, obviously the moment I know these conditional probabilities, that essentially tells you about the forward process. Okay. Now let's say I want to talk about something about the past. In a sense, after observing something here, what I can talk about its previous state. So that means that is what we call retrodiction of the inferences. Okay. For example, let's say, think in this way. If I find OA, that means 0A here, well, I cannot deterministically say as such, well, whether this 0A appears from 0S or 1S. Well, obviously with a probabilistic way you can at most say, but obviously from a deterministic point of view you cannot really infer. But here if I find 1A, at least from here I can directly say that, well, if it has to appear, it must have to be coming from here. Okay, so how mathematically you essentially claim this actually comes from something called the Bayesian inversion, and where implicitly the Bayes rule I have used. So if you think in this way, this is the forward conditional probability, then I multiply with the initial probability with which this 0s is appearing, and then dividing it by the probability that I'm having here on the other side, and based on that I actually find out the reverse or retrodicted conditional probability. And the moment I find this probability to be 1, that means it says that if I see IA, that kind of deterministically infer that it must have to come from this JS. So this is how you actually talk about this inference in the deterministic sense, obviously in the classical domain. And now the question comes, obviously you can understand here that you kind of need a prior information in order to do this inversion, because you see I need this probability here. So that means I use the initial probability, and because of that I also get a final probability, and kind of I need a prior information in order to do this retrodiction of the Bayesian inversion. Well, now the question comes how one could extend this thing in the context of quantum evolution and so for the quantum inferences. Well, we know that the probabilities are extended to density matrices, because at this moment we are not just dealing with the probabilities but also the superposition in different bases, which is allowed in quantum mechanics. And also it is kind of expected that these conditional probabilities also need to be upgraded to something called causal conditional states. And now we will explore how one could extend it or actually find out these causal conditional states. So let me start with a general map. Let's say this is a lambda, and when I say general map, it means like completely positive trace preserving map. And let's say it operates on a Hilbert space denoted by S, and it gives output on the space R here. And actually for this particular operation, the causal conditional state is actually expressed in this way. If you look it carefully, you will find that this is nothing but like you make a partial transpose over the Chua-Jammikowski matrix. Okay, that is what you have done. And now if you say that, well, can I use this conditional state at least to talk about my prediction, in a sense, the future state that I'm going to have in case I have this input rho s here. Obviously, in the level of state transformation, it is nothing but you apply this rho s on this lambda on this rho s and you get this one. And that also you can find using your causal conditional state through, so what you do essentially, there is something called star product. So you make a star product with your input state, and then you trace out the s degrees of freedom, and then finally you essentially get this rho r. So this is essentially the reverse map of Schwarz-Minkowski isomorphism. Okay, and obviously this particular product looks little weird though, but somehow it turns out to be a consistent one. So now if I think in the similar way like I did for classical conditional probability, and I try to invert it so that I can use them for my inference, what I will do essentially is like you have your conditional state. It's kind of like you are multiplying with the input probability and dividing it by the output probability. So this is how somehow you kind of inverting the process, and that's how you actually get the conditional state corresponding to the reverse operation. Okay, obviously it's interesting though, but it turns out that if you look at this causal conditional state and you find out its corresponding operation, this operation turns out to be the phase recovery map of this particular channel. And obviously the phase recovery map that depends on this input, because once I know this rho s, obviously I know this rho r, and with respect to that you can see that, well, this is kind of a function of rho s. So phase recovery map in general we know is not a unique one, but if you know little bit about your initial state, you can always come up with this phase, the reverse map. And the interesting point that I shall be restricting today mostly is the case of unitary operation, obviously. And what actually is only recently people prove it explicitly that for a unitary map, your phase recovery map would be just the inverse of it. Okay, and it actually does not depend on this prior state what I was mentioning. So in case of non-unitary operations, what people do is essentially either choose this reference state, they call it reference prior, to be maximally mixed state, which is like the unbiased prior, or they look for some steady state given the operation and use them as like their input state. Okay, but for unitary it's kind of independent of this prior, so you just take your U dagger, and that kind of gives you the phase recovery map and correspondingly your Bayesian inverted state. Okay. So with this, now I will go quickly how even with this simple setup and considering just unitary, you can find some differences in particular in inferences when you consider your Bayesian classical Bayesian inference and quantum Bayesian inference. Okay, so here I will take a simple example to start with. Let's say I have a bipartite, let's say isometry, or for simplicity you can consider even the unitary, that takes my object from this Hilbert space to this Hilbert space, and this is how this isometry actually acts. So if my system state is in 0, it doesn't change the apparatus, or let's say a state, but if my system state is in 1, it actually goes to a plus state. Plus state is the equal superposition between this 0 and 1. Okay, so it's obviously you understand it's kind of a control unitary, but not in the same way like you have control not. Okay, and now say you start with your system state in this form, which is having some superposition between 0 and 1, and then you club it with the state coming from A, so that means the initial state is uncorrelated, and then you apply this global unitary. And then from here, you can equivalently write down the action of this operation in this way. And now, let me just quickly also mention on the level of classical probabilities what is actually happening in this operation. Whenever I have this 0, 0 here, it remains 0, 0, but whenever I have this 1, 0, I go to, with this probability 1 minus r and r to 1, 0 and 1, 1. Okay? And obviously from here, once again, if I just consider, just a minute. Yeah. So, excuse me. Yeah. So, obviously from here, if you see that if I observe this particular state as my outcome after the evolution, it kind of deterministically infers that it must have to come from there, because you have no other choice. This is what your classical Bayes rule essentially tells you, and actually you can just quickly calculate using this, that if you start from this state and you invert it, that means you just try to infer what was there before, it actually comes with unit probability. Okay? But well, in the quantum domain, if you think or come or make use of this quantum Bayes retrodiction, which is in a simplest way, if you look at it, it is nothing but applying the observed state with this inverted unitary, you immediately see that this is not equal to this one. So it has something else actually. Although it doesn't look so important here, but in the examples that I will be considering for Frauchiger-Renner and Hardy's paradoxes, you will see this thing will be crucial actually. So this is where we first see kind of a disagreement between quantum Bayes based retrodiction or quantum Bayes based inference and the classical Bayes based inference. Okay, now I shall be taking a little bit different example here. What I will be doing, I have kind of a unitary evolution, it's kind of unipartite, and it takes your state from A to B. And the action is essentially, as you can see, probably that this is nothing but like beam splitting kind of operation, right? So this is what you have. And now, unlike previously I was considering uncorrelated state to start with, I will start with an entangled state, okay? And my initial state is essentially this one. And now I will apply my local unitary here, and the final state, which again can be written down in this form after a little bit of rearrangement. Okay, so once again, on the classical level, what is happening is exactly I've just written here, and I would like to look at the cause or the states that were responsible for this particular state to appear. For example, the cause of this particular observation. Well, from here you can immediately see that if I see this particular state to appear, it kind of deterministically says that, well, it has to come from here. Although one may say that, well, this is appearing with 1/6 or 1/6 probability, right? But whenever it appears, I can deterministically say that it must have to come from here, at least from the classical Bayes theorem. Okay, and you can understand that whenever I see that, the conditional probability after you do this Bayesian inversion, it actually gives you 1. Well, it turns out to be, it's not true again, because if you just take this state which you have observed and you just apply this local unitary here, and it's actually this state, not this one. So once again, you can see in the simplest way that you're even just considering the just unitary evolution and so that it does not comply with your classical Bayes or Bayesian retroduction or Bayesian inference. Well, now I shall go towards using these two observations and try to apply on this Frauchiger-Renner paradox actually. Well, it's normally very difficult to explain this paradox, and it's written also in a very complicated way, but here I try to put things a little bit in a systematic way, at least according to me, so that you can follow. So here the first step in this particular setup, so you have a qubit R that is prepared in these two states where HR and TR are orthogonal states, okay? It's a qubit. And then what you do, you kind of apply an isometry, and you kind of quickly see that this is the first example kind of unitary that I have taken. So if this one is in HL, the spin down state remains spin down, but if it is in TR, that means this TL bar is T, so, and this kind of gives you equally superposition of up and down spin. Okay, this is essentially you have. And once you apply this particular isometry on this particular state, you essentially have these two, this state, which can be expressed in an equivalent way, where the bottom line is written using this additional, let's say, in this form where TL bar is like the superposition of FL bar and L bar. Okay, so this is what you have done. And then finally you apply an isometry on this particular state where it just changes the S part, this S part to this form. It's just again some kind of a plus and minus state. So that the final state is essentially written in this form. Well, I know that it's not very easy to really follow all these things, but for the time being, you just rely on me thinking that, well, these are the states after you do all these transformation, okay? And now let me go one by one how these statements, in particular coming up with the contradiction, comes through. So for example, let's say you first see OL bar. See, the moment I see OL bar, I kind of infer that it must be observed in association with this upspin, because this OL bar is absent here, so it's kind of the orthogonal subspace, right? So whenever I find OL bar, I must see upspin. There is no other choice. The second statement comes that whenever I see upspin, I should see this TL bar, because I don't see anywhere else upspin, right? And then you say that, well, whenever I see TL bar, it must have come from here, TR, right? And then you say, whenever I see TR, it should give rise to this one because of this. It should give rise to this right arrow S. And once you see right arrow S, you apply this one, you immediately see that it has to be associated with, or this is nothing but your FL. So this means this, when I apply this isometry, that means summing over this, and you understand these two will survive, the rest will just get cancelled. Okay? So in total, what it says that whenever you observe this OL bar, although it will be observed, let's say, with 1/6 probability, but whenever it appears, whenever it clicks on my detector, I can, at least following this argument, deterministically say that it has to be associated with FL. There is no other choice. So that means, in principle, I should never see any state in my this final state which is like OL and OL bar. Because whenever I see OL, it has to be associated with this one. But what I see here, that this OL bar and OL are observed with 1/12 probability. So this is where is the contradiction. And this is essentially the essence of Frauchiger-Renner paradox. Is that thing clear? I know that there is a lot of juggling with the statements. Is that thing clear? Yeah? Well, what I wanted to say is that if you start from this, then it kind of, through these statements, it kind of tells you that, well, you can never observe this particular state. Well, you can observe this particular state, obviously. The interesting point here is that that all these arguments, what Renner and Frauchiger made, are based on classical Bayes theorem. So that means whenever you say that I observe this, that implies I observe this one, and this, whenever I observe this, it implies this one. It's kind of a classical statement, classical Bayesian based inferences that you actually make. Okay? And the question comes that, well, is it really true that is happening in the quantum domain? It may be that one has to go beyond these classical inferences in order to make this deterministic statement, and has to apply quantum Bayes rule. And it turns out that, yes, this is exactly the case. So in order to really show that, you can just consider this particular statement. For example, let's say, I think I started with this one. Yeah, this one, this particular statement, that if you observe this one, does it really imply that you came from this TR or not? Okay? And for that, I essentially broke this isometry into two different parts, where first one is just nothing but changing the space, and the second one is nothing but the control unitary kind of operation, which is exactly similar to the first example that I had considered. Like whenever my HL is there, this spin does not change, but whenever it is TL bar, it goes to an equal superposition of up and down. Okay, and obviously from there you kind of see that, well, if you start with this state, that means this state, and you apply just the reverse unitary or inverted unitary, it is actually of this, it's a state of this kind, it's not this one. So that you can really claim that this observation of TL actually is coming from this TR. So that means your deterministic argument based on which you come to this contradiction actually fails. And then once you start from there, you just apply your V2 and you see that obviously you can see this particular state. So a priori there is no, from here itself I can say that there is no contradiction actually. And well, this is again just to start from here also you can show that it takes you to OL and OL bar. So that was essentially to kind of tell you that if you start quantum Bayes rule while you try to make an inference, you apparently, at least for Renner to Renner case, don't see any contradiction. Okay, so that is the first thing. And the second, I have some time now. Okay, so now I will go towards Hardy's setup for the paradox in particular, but let me also clearly mention that while we say we reconsider Hardy's paradox or Hardy's setup, we actually accept my quantum mechanics is non-local. See, in Hardy's setup, they normally look at the local outcomes and based on that he tries to infer about the other. But here I will be considering like quantum mechanics is non-local, so that means it's allowed to have a global observation and based on that if I can infer something. So obviously that is kind of a deviation of the things what Hardy did. But the setup in a sense that the unitaries and the states I shall be considering it essentially very close to the one they have considered, the Hardy had considered here. So once again I start with this bipartite state where the parties are denoted by plus and minus, and this is some kind of a very particular choice of this initial state. And then I actually, so this U and V, these are like orthonormal states that's mentioned here, and I apply actually beam splitting operations where this U plus or minus goes to D plus and minus in this form. Okay, but these are like the local unitaries that you have. And then you have three different ways, or let's say three different operations. First, you apply this unitary here on the first party, that means the plus party, and you get that. Then you apply this one on the second party so that you finally get this one, right? So it's essentially, you can do something like that. You start from here, you apply this, and then you apply this, or you start from here, you apply this, and then you apply, so that you go to the final state, but in two different ways. Okay? So this is essentially the operation that I'll be considering in this case. And now let me start coming to the statements. For example, let's say I see this particular state, and I see it with 1/12 probability. So obviously, maybe out of 100 time, 100 repetition, maybe I will get 100, how do you say, 1/12 times 100, 100/12 times I will see it, okay? But whenever I see it, what I can talk about for its previous state. So essentially it says that whenever I observe this one, this global state must be there in this particular step. In Hardy's argument, what it does is essentially says that, well, if I see D minus here, this D minus must have to come from here because from here to here, I did not do anything on the minus part. I have just done whatever on the plus part. So that means this minus part should not get affected. So whenever I see D minus here, it kind of uniquely or deterministically, you can claim that it has to come from here. But for me, I just don't care about this local argument. Rather, I will go saying that, well, whenever I observe this one, in the previous instance, the state must be coming from here. The reason is that, again, the classical inference, classical Bayes rule based inference says that the conditional probability of finding this one from here is actually 1. So essentially, you do the retrodiction, classical Bayes retrodiction, you will see that this kind of deterministically says that it has to come from here. There is no other choice. And now, once I see this U plus, again, it has to be there. That means it says that, well, there must be a U plus state in this initial state that I had started with. The reason is that from here to here, from here to there, I did not do anything on this part, plus part. So it should remain unaffected, right? So it actually says that whenever I see D plus and D minus in this final state, there should be U plus in the initial state. And the similar argument I also can make that if I see this one, it must have come from here. That means if I make a deterministic inference from the classical Bayesian point of view, that must be coming up with one unit probability, this unit conditional probability. And again, that kind of infers that this U minus, if I see here, it has to come from here. So now together, if you say that the first one says that D plus and D minus in the final state demands U plus in the initial state, D plus and D minus in the final state again demands U minus in the initial state. So together it's kind of ask that I should see U plus and U minus in the initial state. And obviously you see there is no U plus and U minus here. So this is essentially the essence of Hardy's paradox. And now obviously you understand what I'm going to talk. I would say that, well, all these arguments that you have made here are actually based on this classical Bayes theorem, or this classical retrodiction in order to infer about where from this state come. Okay? And it turns out that obviously from the quantum Bayes theorem point of view it's not true, and you can just simply take this particular example and you just, let's say you start with this one and you apply your reverse unitary, that is essentially making this classic Bayesian quantum retrodiction, and you see that, well, it not only comes from here, it also comes from there. At most with half probability you can say, you can never say a deterministic argument saying that this must have come from here. Okay? And now you understand that in a similar way the argument I made from here to here also is wrong. Okay? And from now you start from here and you apply this global, the reverse unitary in both cases, and you will see that obviously you will find some state here like this. Okay? So that means it kind of says that if you take into account this quantum Bayes theorem in particular while you make the retrodiction, there is no contradiction actually. So this is essentially the message, and now I would like to conclude. First, what we have seen that the classical Bayes rule is kind of inadequate, but we all know, because in quantum mechanics we know that there is this contextuality, and so that means the classical Bayes rule actually doesn't work. And we also could show that even in the kind of a setup of Hardy's like paradox where we consider quantum mechanics to be non-local, you can also have these contradictions, but these contradictions are solely from coming from this limitation of classical Bayes rules. Okay? And then essentially what we want to claim is that the kind of contradiction people like Frauchiger-Renner got actually is not at all a contradiction, it's a mistake they have made by considering classical Bayes rule while making their statements. And how to resolve it also just by using quantum Bayes rule we have just kind of demonstrated, and that's all for the time being. Thank you very much. Yeah. Mm-hmm.
So the usual formulation of this Hardy paradox is in terms of this local reliable theory, so it just involves some probability distribution, and you see that you have some sort of kind of logical implications, and then you get this contradiction. So you kind of here you reformulate it in terms of these states and this inference. So could you do the same also in terms of this local environment?
Yeah. So. So the point is that this is not exactly where I'm considering local. I'm already considering. See, I'm making an observation of the global state and making an inference about also the global state. So I'm really not taking into account this local structure here. Okay, but even if you consider where the difference comes, see on the level of classical Bayes theorem, you just deal with probabilities. You ignore the state that you have, let's say, observed. Correct, so correct.
And that's why in quantum case you have this unitary, you just
correct.
Just don't invert this thing in a fixed space.
Correct. So let me give you said a very interesting point. Let me just tell you, see this, come here. You started with this one, that infers the spin state should be up. This up spin, see, I did not do anything. This up spin again says that the state of L bar should be TL. You see, they are not the same, no? So you started saying with a kind of a countering argument, it says that, well, if I say see OL bar, it implies I see TL bar. Understand why this is happening? Because quantum mechanics allows superposition, which is not allowed in the classical case. In classical case, you never have this situation. So that means you have to take into account also how you this property of superposition in the when you deal your object in the quantum domain, right? And classical Bayes rule does not take into account all these things. But the quantum one, they obviously take into account all these things. Does it answer to some extent? Yeah.
Yeah, I don't know. I was just more wondering why is the connection with it, or if in the original formulation in terms of local interpretable model, does inference play a role or not? Because I don't see that.
See, it's not very easy for me to really translate it into this local structure because I don't impose anything here. It just says that, okay, I give you some evolution in different steps. I observe something, and based on that, what I can say at the time t minus 1, let's say. Okay. So on the other side, what I want to say that what is so special about quantum Bayes rule? It actually not only take into account the probabilities, but also the observed state. Because when you invert, you don't only do your calculation with the probabilities, but also you take into account the observed state that you have, and then you invert. Yeah. Yes, please.
According to your definition of like this quantum inference, like this contradiction doesn't work here. Can you go to the Hardy's slide?
Yes, yes. Yes.
Like where you have no contradiction.
Okay, very good.
Like, so like this classical Bayes rule, you say you have a contradiction. I was wondering, like, it seems like this 1/2 seems pretty generic, or it seems that usually you have probabilities there. So with this quantum Bayes rule, what can you infer? Like, when do you actually have probability 1 to do like an actual statement?
So if this thing turns out to be 1, then only you can make a deterministic prediction saying that, well, if I observe this one, it must have come from this one. Otherwise, your argument would be probabilistic only. You can at most say, well, with half probability, it may come from some this one, and half maybe something else.
So just for me to understand, like this 1/2 means you cannot basically use this contradiction or like the statements that let you.
Yeah, so the statement which kind of deterministically says that, well, if you observe this one, then you must have observed that. This deterministic statement is wrong.
Okay, but then like what can you infer from your quantum Bayes rule? Like in which cases do you actually?
So you say that, well, for example, if I see this one, then it must have come from this one. Because from here to here, you can show that this quantum Bayes conditional probability is essentially 1. You just do the inverted one. If you see this one, it must have come from this one, not just this one. Does it answer? No.
Yeah, like, okay, but I think at least to some extent, like some classical reasoning you can do in Hardy's paradox. Like for example, like given that you find like D plus or something, let me do it. Like given you find D minus, and like you measure actually the plus particle in the like in the computational basis, in the U and what is it, U and V. Then you always find U. So to some extent you can do a classical reasoning in Hardy's paradox.
So actually, I don't want to really invoke this local realism here because it has always something to do with some prior assumption. No? For example, you already start with local hidden variable theorem, and all the probabilities that you deal with are classical probabilities, and you always take into account that your Bayesian rules are correct. So that is why I really don't want to really say something here, because while I was thinking about that, if I invoke quantum Bayes rule inside Hardy's setup, what you may see actually turns out to be, it's not very easy to say something very precise, at least, because you see a contradiction, and this contradiction is coming from, let's say in this way, either violation of local realism or maybe violation of this Bayes rule, but you cannot really figure out from where it is, or maybe altogether that result in this contradiction. But in this case, since I don't assume this local realism thing, so I can just say that, well, you don't need to really think about, so if this is there, this is there, but on top of that, your classical Bayes rule is somehow inadequate, just simply like this.
Okay, yeah, maybe it's, I'm not expressing myself clearly. Okay, what like, it seems like this classical Bayes rule is too strong, but this quantum Bayes rule seems too weak for me. Like,
weak.
yes, so like I would like to know some more properties of this quantum Bayes rule, because this like seems to me inherently probabilistic, and probably only if you like measure in the same basis you can actually do a statement. But sometimes also in quantum mechanics you can do some, like, I would say, like very basic Bayesian reasoning. So
I'm not.
Whatever, maybe we can.
Yeah. So I'm not very clear. So let me tell you one thing. So if you have a dynamics where the dynamics itself is kind of it can reproduce classical dynamics, in a sense, classical stochastic diagonal thing. Your states are also diagonal in the sense like there is no superposition. Obviously, your quantum Bayes rule immediately converts to the classical one, but not otherwise. As I was mentioning here, I think in the simplest scenario, as I said, I'm sorry, just give me a moment. Here, for example, let's see in the classical sense, if I observe this one, it kind of immediately tells it has to come from here, right? But in quantum case, no, it's something else. Sorry, it's completely something else. Actually, this particular state comes from here, not from there, right? I still don't need to really go for these statements here. Just simply what you can. So it's a question of like, I observe this, based on that, what I can tell about my past.
Do you have a paper?
No, it should come in a week. Okay. Yeah? Okay.
Any more questions for the speaker? No? Okay. So that's
Thank you. I think you have to.
More than last time.
Yeah, maybe you have to switch off the YouTube stuff.